Hello there, Mrs. Saunders here. Welcome back to the Epic Saga of Calculus, where mathematics meets drama. And sometimes the drama is more explosive than the math itself. When we left our story last time, Newton and Leibniz had independently invented calculus. They had fought bitterly over who deserved the credit and left the mathematical world forever changed. But here's the thing about revolutionary discoveries. It's not enough to just invent something. You have to convince the world to use it. And that, my friends, is where notation becomes everything. Mathematics isn't just about ideas. It's about communication. The symbols we use are shorthand. They let us think faster and see patterns more clearly. When Newton and Leibniz created calculus, they gave us two completely different languages for talking about change and motion. And like any language war, this one would have winners, losers, and consequences that lasted for centuries. Isaac Newton thought of calculus in terms of flowing quantities, variables that changed continuously over time. His notation reflected this perfectly. If x represented position, then x dot represented velocity, and x double dot represented acceleration. It was clean, it was intuitive, and it was directly connected to the physics that he cared about. For Newton, this wasn't just notation, it was philosophy. The dots literally represented the flow of time. When he wrote x dot, he was seeing the variable x streaming through moments, changing instant by instant. But here's the problem. Newton's notation, it was tied to time. So what if you wanted to find the rate of change with respect to something else? Newton's dots suddenly became awkward. Meanwhile, Leibniz had created something far more flexible. His dy dx notation looked like a fraction. And that wasn't an accident. Leibniz wanted mathematicians to think of derivatives as ratios. Tiny changes in y divided by tiny changes in x. And this notation worked for any two variables, regardless of what they represented. I mean, consider the power of this approach. Do you want to find how pressure changes with volume? Write dp dv. Need the rate of change of profit with respect to production? Write d pi dp. Leibniz's notation adapted instantly to any situation, making calculus feel less like physics and more like pure mathematics. Even better, dy dx behaved like fractions in many calculations. To be fair, this wasn't mathematically rigorous. Dy and dx, they're not really numbers, but it made calculus feel intuitive and it helped mathematicians to avoid errors. After the bitter fight over who invented calculus first, with Newton's supporters claiming Leibniz was just a plagiarist, and Leibniz's supporters firing back that Newton was just trying to steal the credit, national pride kicked in with a vengeance. British mathematicians loyal to Newton stubbornly stuck with his dot notation. Continental European mathematicians, they embraced the dy dx symbols. This wasn't just preference, though. It was mathematical nationalism. The Royal Society had declared Newton the true inventor of calculus, and they were going to prove it using his notation. But the truth is, the dy dx notation, it was simply better for most mathematical work. While British mathematicians struggled with that awkward dot notation, their European counterparts were racing ahead using the more flexible system. Enter the Bernoulli brothers, Johann and Jakob, two Swiss mathematicians who became the great champions of Leibniz. The Bernoulli brothers became mathematical ambassadors for Leibniz's methods. They wanted to prove that Leibniz's approach could solve problems that had stumped mathematicians for centuries. In 1696, Johann would issue what might be history's first viral math challenge, the Christochron problem, which we'll explore more in episode 4. Meanwhile, Jakob was developing rigorous tools for mathematical optimization. The Bernoulli brothers weren't just defending Leibniz's notation, they were about to show the world what it could actually accomplish. Merchants would optimize their shipping routes for maximum profit. Engineers would design the strongest beams with minimum materials. Navigators would plot courses across those treacherous seas using nothing but mathematical precision. For nearly a century after Newton's death, British mathematics just stagnated. And the irony is heartbreaking. The nation that produced Newton fell behind in the very field that he had helped create, while continental European mathematicians, they flourished. For example, Leonhard Euler, the Swiss mathematician who became arguably the most prolific mathematical genius who ever lived. Euler used Leibniz's notation throughout his career, just cranking out mathematical discoveries at an almost superhuman pace. He could work so efficiently partly because Leibniz had given him such a powerful symbolic tool. And fun fact, Euler was actually blind in his later life, but we'll get to him in future episodes. Meanwhile, British mathematicians found themselves increasingly unable to follow the continental developments. Papers written in the notation of Leibniz looked just foreign and impenetrable. Mathematical collaboration across national lines became nearly impossible. Britain was just cutting itself off from the mathematical renaissance happening just across the English Channel. This situation became so bad that some British mathematicians began secretly learning Leibniz's notation just to keep up with European research, but they couldn't publish it. That would be a treason to Newton's memory. By the early 19th century, the situation had become ridiculous. British mathematics was decades behind, and everyone knew why. So finally, a group of young Cambridge mathematicians, including Charles Babbage, the computer pioneer, John Herschel, and George Peacock, they decided enough was enough. In 1812, they formed the Analytical Society to convince British universities to ditch Newton's dot notation and start using dy/dx symbols like the rest of Europe. Their motto was a bit cheeky: to promote the principles of pure deism as opposed to the dot age of the university. They were basically saying, let's use D's instead of dots, because sticking with dots just makes us look old and out of touch. It was a mathematical rebellion, and it worked. Gradually, British mathematicians began adopting continental methods and notation. The walls of isolation started crumbling, but the damage was done. An entire century of mathematical progress had been lost due to national pride and notational stubbornness. The notation war was over, but the real battle was just beginning. Because now that mathematicians had the right language to express calculus, they faced a new challenge, proving it actually worked in the real world. Could these abstract symbols and formulas really solve practical problems that had stumped humanity for centuries? Could calculus design better ships? predict the motion of planets, and help merchants maximize their profits? Johann Bernoulli was about to find out. In 1696, he would issue a mathematical challenge so compelling that it would draw Newton himself out of retirement and spark a problem-solving revolution that continues to this day. Next time on the Epic Saga of Calculus, we will get to see genius applied to real life. Thanks for being here.